Hello everyone, I'm Xu Jiangxiang, a PhD student from HPCA'26. Today I'm going to introduce my work VAR-Turbo, unlocking the potential of visual autoregressive models through dual redundancy. While diffusion models and visual autoregressive models both can achieve high-fidelity imagery synthesis through iterative refinement, VR models exhibit two superior capabilities over diffusion models. First, scale-out seamless multimodal integration with large language models, and second, scale-up power law scaling behavior. However, the generative process of VR model is quite time-consuming. As you can see in this slide, VR's inefficiency stems from two levels. First, at the inter-iteration level, VR model generates one visual token per iteration. Therefore, it probably needs more than 1K steps to generate a single image. Second, at the intra-iteration level, VR model employs a compute-heavy generative vision transformer at every iteration. To minimize the prohibitively long generation latency posed by VR models, we propose our work, VAR-Turbo, which features three algorithmic innovations aiming at reducing the computational costs of VR models. First, at the inter-iteration level, by leveraging the image redundancy, we propose draft-free pair decoding. Second, at the intra-iteration level, we capitalize on the model redundancy and further adopt a hybrid optimization scheme. Specifically, in the shallow layers, we propose an adaptive hierarchical attention called token aggregation. In the deep layers, we use a more aggressive technique called dynamic bypass. At the hardware side, VAR-Turbo has two unique hardware units. First, unified attention core, and second, radical source core, to efficiently support the previously mentioned algorithm pipeline. First, draft-free pair decoding. Basically, our proposed draft-free pair decoding only involves top K operation to decode the most confident top K visual tokens, and therefore is draft-free. This slide shows token aggregation, a hierarchical attention method. First, small attention, it aggregates neighboring tokens information and generates one representative token that represents its respective local window. Second, big attention, which combines information from all the representative tokens generated by the small attentions. This slide illustrates the working process of dynamic bypass, which selectively skips the whole transformer layer for those unimportant tokens. And this slide shows the overall architecture of VAR-Turbo accelerator, which has two innovative cores, attention core and radical source core. Attention core is a highly reconfigurable core to support the heterogeneous attention proposed by token aggregation, the small attention and the big attention. Radical source core employs locality-aware scheduling to efficiently support the large-scale top K operation introduced by draft-free parallel decoding and dynamic bypass. Through the synergy between software and hardware innovations, VAR-Turbo achieves orders of magnitude higher speed up and energy efficiency compared to NVIDIA V100 GPU and Intel's CPU. Then, according to the roofline model analysis, VAR-Turbo approaches much closer to the computational roofline than V100. Then, compared to SOTA vision transformer ASIC accelerators, VT-Coding and adaptive VAR-Turbo delivers 6.1 times and 3.8 times higher throughput, and 6 times and 7.8 times higher energy efficiency, respectively. At last, thanks everyone for your precious attention.